people around them. We can provide. Without much further ado, Tyrus, the audience.
Thank you. So let me thank first my co-author, Dimitris Giannakis, who was a big part of this work, and also NSF for supporting me. It's a great honor to be talking FFT. I presented a poster back in, I think, 2011 that was sort of launched actually all of this work when I presented a poster at FFT, and Koifman came and talked to me and said I should be using his method, and I spent the next 2 years carrying his diffusion maps paper around. So of course I've learned since then that a lot of great work being on, and I should also thank the previous speaker, Maya, because perfect lead-in to something I'm going to talk about, and hopefully I can answer or provide a possible answer to the final question of one way that you could try to analyze vectors on graphs. So, so I sort of came to this through, I actually came to this from dynamical systems, where we're trying to learn dynamical systems from data. So coming from sort of data-driven world, but of course we want to consider data quite broadly. And so what is, most data comes with some measure of like similarity or dissimilarity. And so like what you get from data typically is kind of like a graph structure, where things are connected if they're similar and not connected if they're not similar. Any more than that, you really got to work to build, right? So you can get a measure if your data comes in a Euclidean space or something like that. You can inherit a measure from the ambient Lebesgue measure and things like that. So all that stuff is floating around, right? There's sampling measures and things like that. But if you want more structure than just a graph structure, you got to work hard. So we want to see what we can wring out of this graph structure, right? We want to get everything we can out of it, because that's what we get almost for free. It's like it's almost has to be there. And so from the graph structure, of course, you can get the graph Laplacian, which is in a sense equivalent to the graph. And so where I sort of entered the picture, as I just mentioned, was diffusion maps, which showed that you can use sequences of these graph Laplacians. And if your data happens to live on a manifold or very, very close to a manifold, you can construct a sequence of graph Laplacians that converge to a manifold Laplacian. And so, knowing what little I knew back then from differential geometry, I knew that, well, if you know the Laplacian, you know the Riemannian metric, therefore you know the whole manifold. So how can I get all this higher order geometric information out of this? Somehow I should have everything, right? And just from these graphs, right, which I get almost for free from having this notion of similarity or dissimilarity. And so that's what the idea of the spectral exterior calculus is. It's a way, how do you get all the geometry of the manifold? Or in some sense, if your graph isn't converging to a manifold, you now have some formulas that you could use inspired from differential geometry that maybe give you ways to talk about tensor fields and differential forms on these discrete structures. So I'm not quite sure how meaningful these formulas become on graphs. We were mostly focused on the case like when you have data on a manifold, do you get the right objects in the limit? So just really quickly, there's sort of some competing exterior calculuses out there right now, and I just want to make the pitch for my method. I'll say some more at the end, but yeah, simplicial complexes are hard to build, right? Like if you hand me some data, you can't. Simplices have to meet strictly at edges, right? And so like if I just start adding simplices, right, you're going to end up with bad intersections like this. You're not going to have a real simplicial complex. So nothing against simplicial complexes. If you can build one, that is a beautiful data structure, right? But they are very difficult to build, especially from noisy data sets like this, right? Try triangulating. I mean, this is a very nice data set, just a torus, but very finely sampled with just a little bit of noise. Very hard to build a simplicial complex. I've tried. Okay, so that's why we want to do all this from just graphs, right? It's easy to turn this into a graph using nearest neighbor type structures and things like that. Okay, so I'm going to present all the formulas that the previous presenter Maya didn't present, but it was a great introduction because it covered all the formulas I didn't talk about. So from the graph Laplacian, of course, that sort of encodes the entire graph. And this is what she was mentioning about what's so important about the graph Laplacian. Well, it encodes this notion of smoothness. Of course, I like my graph Laplacians normalized. So I talk about this generalized eigenvalue problem. Right, it's equivalent if you move the d over to the other side, you have the normalized Laplacian. But this keeps everything symmetric, right? If you have a symmetric graph. But okay, so your eigenfunctions, right, on your graph are minimizing this functional, and as was pointed out, right, this is a functional that measures sort of roughness. And so if you're minimizing this, then you're making nice smooth functions that, basically if two nodes are connected by an edge, an eigenfunction with a small eigenvalue will have to change a very small, amount as it moves between those two nodes. So you're trying to find this nice smooth functions. And as was previously mentioned, this gives you the tools to do convolutions. There's also some amazing work people doing wavelets on graphs, which it was also very inspiring. So we have sort of harmonic analysis on all these graphs, and in the same way, right, and sort of with this analog in the continuous world, you have the Laplace-Beltrami operator, which, as I mentioned, because it encodes the Riemannian metric, encodes all the geometry of the graph, so of the manifold. So in a sense, the Laplace-Beltrami operator tells you everything about the manifold. And so that was kind of the big, aha moment for me, is like, if you want to learn a manifold, don't go out there and try to learn sets, don't try to learn the set that it lives on. Don't try to learn a function that describes the manifold as a set. Don't try to learn the manifold by finding a bunch of tangent spaces. Just get the Laplacian, right? That's a nice description of a manifold, right? It's an operator. So it's a functional analysis type operator theoretic description of a manifold. Okay, so of course, the eigenfunctions form an orthonormal basis for square integrable functions on your manifold. That's nice. We've got a nice orthonormal basis. But what's so great about this basis, right, is again, it's a basis that encodes, right? There's an energy that you're minimizing, and you're getting a notion of smoothness, right? So this gives you sort of a natural way to talk about harmonic analysis. And again, you can define notions of convolutions and wavelets. Translation, of course, is the hardest one, I think. Because if you have a group structure, then your translations act nicely, right? You have, they have a group action, but if not. And so this is sort of how things go. So, here's a simple graph where you just have a few data points that happen to live on a circle, right? So I think there's 10 data points on the unit circle. So you build we build a weighted graph using a kernel function. And this is really, it's really interesting. There's sort of an RKHS happening sort of in the ambient space. But instead of sampling points uniformly on the ambient space, you're sampling points from this singular measure, right? Because the measure is concentrated on this manifold. So it's not absolutely continuous with respect to Lebesgue measure. But somehow by sampling points on this singular space, singular measure, your kernel is restricting to this RKHS that lives on a manifold, at least in a limit, or converging to something like that. But anyway, so you have this kernel matrix, and I'm not sure, this seems like it might be related to the graphon, but that's, my knowledge of graphons is a little shaky. So you have this kernel matrix, you do the right kind of diffusion maps normalization, you get a graph Laplacian, a special type of graph Laplacian, and you can look at its eigenfunctions, and they look sort of like sines and cosines, but of course we don't have much data here. So you crank up the data, put 100 points on the circle, of course very nice points, right? Nicely sampled points. You get things that look a lot more like sines and cosines, and the eigenvalues of the graph Laplacian start to approximate the eigenvalues of the Laplacian, the Laplace-Beltrami operator on the unit circle. So of course, there's all these convergence results that lots of people have been working on for a long time now, spectral convergence being the hardest. So of course, but you can do this on other types of graphs, and there the eigenfunctions sort of encode things about the symmetries of the graph. So this has like a Z3 symmetry, and that shows up in the eigenfunctions. Here's a graph that lives on a sphere, right? And you get some really interesting, cool kernel functions. And again, there's repeated eigenvalues here, right, that talk about the symmetry of the sphere. But more generally, you can just have some data that lives on some crazy manifold, right? How are you going to figure out what the Laplacian? I mean, even if I knew what this manifold was, it would be hard for me to construct the Laplacian, right? But just you build a graph on it, right, and do diffusion maps, and you get your Fourier basis, and you're off to the races. All right, so we've got our Fourier basis. We've got some way to do, at least a way to do harmonic analysis on manifolds. Now I want everything else, right? So I want the exterior calculus. And so what is that? It's the calculus of tensor fields and differential forms. In theory, it can be built entirely from the Riemannian metric, which is entirely encoded by the Laplacian. So let's see if we can make that work. And so this is what's really cool about this area that sort of is developing, and there's so much work going on, but I think there's still a whole lot of low-hanging fruit here, right? Where geometry meets harmonic analysis and functional analysis and operator theory. There's just like, how does the geometry influence all these things? It's really a cool phenomenon. For example, I think Feikinder and Grokenig are proving some things about sampling theory on manifolds now, and it's just really beautiful work. But okay, so what's so great about this? Well, we can talk about, Stokes' theorem, right? In the context of the exterior calculus, right? We've got all these beautiful theorems from differential geometry. We can talk about, like the Lie derivative is really crucial if you're talking about nonlinear observability and controllability, right? It's all about Lie derivatives. Lie derivatives are really hard to compute, right? On manifolds, especially. And then cool things like the Hodge and Helmholtz decomposition, that's where we talk about vector fields, right? So now you have a vector field on a graph. Can you decompose it into like the gradient part and the divergence free part? Is there some notion of that on a graph? That would be really cool. All right, so here's the strategy that we're going to take. We're going to start from either a graph or a manifold. From either of those, you get a Laplacian. From the Laplacian, that's equivalent to its eigenfunctions and eigenvalues. And so the goal is really to build an exterior calculus using just these eigenfunctions and eigenvalues. Just build the exterior calculus from the harmonic analysis. Can we do that? Well, okay, so we're going to reason backwards from what you can do on a manifold and hope that that makes sense on a graph. And there's still, that's where I'm not a graph theorist. I have no idea how meaningful these things are on graphs. I'm just working backwards from the formulas that work on manifolds to get the formulas that, hopefully those formulas will inspire the right formulas for graphs, for understanding graphs. All right, so here's the key, right? So this was just, sort of an afternoon calculation, right, that I want to take you through that inspired this entire idea. And so the idea is, how can you get the Riemannian metric from the Laplacian, right? So this is sort of the most fruitful way to go about it. There's other ways as well, but so if you take the Laplacian of a product of two functions, you get this kind of product rule. But then you get this correction to the product rule because it's a second order differential operator, and this correction involves this dot, which is really the Riemannian metric on a manifold, right? So here's the Riemannian metric between two gradient fields, right? So if I have two functions or if I have two gradient fields, right, I can compute their dot product as long as I can compute the Laplacian. Okay, so we turn this formula around and we say, aha, the Riemannian metric of two gradient fields is just this formula, right? So as long as I can compute Laplacians, I can compute the Riemannian dot product of two gradient fields. And notice this is a global formula on the manifold. This is not like, this is true at each x, right? But this is sort of happening globally. It's sort of a way to do global analysis. Okay, there's lots more vector fields out there than just gradient fields, but we'll come to those in just a minute. That's where things get interesting. But here's what really makes this quite nice, right? When you do this in a harmonic analysis using eigenfunctions of the Laplacian, right? Of course, lots of stuff simplifies, right? Because you've just got Laplacian of an eigenfunction, so you just get some eigenvalues, right? But there's still some nasty stuff hanging around, right? I've got products of eigenfunctions. So here's what's maybe a little bit the first new thing that we need, right? Which is that we need not just the eigenfunctions and the eigenvalues, but we need to understand the algebra of function multiplication on our manifold or on our graph. Okay, so I need to understand that, right? And so how am I going to do that? Well, we run off to see how do you understand, C infinity rings on manifolds. Well, you encode them in these things called the structure constants. So, if you take any smooth function, right, you can write it in the Fourier basis. You multiply two functions. That's just, you're going to get this product, which involves products of eigenfunctions. So all I really need to understand is products of eigenfunctions, right? And so, but of course, how I'm analyzing the product depends on the choice of basis that I've made, right? And I've made this special choice of basis. And so in this choice of basis, I can encode the product by just saying, well, okay, the product of two smooth functions is again a smooth function, so I can write it in the Fourier basis too, right? And so it's going to have some coefficients, right, which are going to depend on the I and j, right, which two basis functions did I start with? And so these Cijks are the structure constants. So it's literally the coefficients of the product of two eigenfunctions in the eigenbasis, right? And so it just has this nice formula, and as long as this is this is completely symmetric. So you can move. This is just the integral of the product of three eigenfunctions, right? But so that encodes the entire algebra. So basically, I can actually from here on out, I can almost get rid of. I'm almost not going to need the eigenfunctions anymore in just a second. I'm just going to need the eigenvalues and the structure constants. But okay, so let's come back to our product of two gradient fields, right? We reduced it since we're using eigenfunctions. We got rid of some of our Laplacian operators. And now what we can do is we can take these two products and write them using our structure constants in the basis. So this is going to be sort of a theme here. Just write everything in the basis, right? You know, I was really good at linear algebra and I took all those lessons to heart. Always write everything in the basis of eigenfunctions if you can. All right, so we take Laplacian. Fortunately, it's a linear operator, so we can move it in here. And look, now we've just got another eigenvalue, right? So that's the beauty of the eigenbasis, right? So we get this beautiful formula, and this is when we started to think that, hey, maybe this is going to work, right? Of course, if you take the inner product of this with phi k, right, you just get this formula here. Now it's an infinite sum, right? So okay, on a graph, it wouldn't be an infinite sum because these would literally, you know, you have a finite spanning set. But on a manifold, this would be an infinite sum. So of course, we're going to be doing sort of a Galerkin truncation of all these approximations. Okay, so that's all well and good, right? But that's just gradient fields, right? There's lots of other vector fields out there that aren't gradient fields, that can't be expressed as gradient fields. And those are sort of the really interesting vector fields that have sort of generate interesting dynamical systems and stuff like that. So what about all those other non-gradient fields? Well, okay, so let's let V and W be two vector fields, right? So let's actually zoom in just a little bit closer now. Take V and W to be two vectors just in the tangent space at a point. So fix a point on the manifold, take two vectors that are in the tangent space. So I can always find a collection of D functions whose these are just like coordinate functions, right? Whose gradients span the tangent space, right? So at a single point, right? So we're fixing a point now. This is just a finite dimensional vector space. I can find some coordinate functions and I can write my V and W in this basis of gradient fields, okay? The problem is that if I go to another point on the manifold, I've still got those functions. I can extend those functions to the whole manifold, but their gradients may not span when I move to another point, right? They may not be their gradients may not be a basis anymore. And in fact, we know that there's examples from the Harry-Ball theorem where you can't find two functions. You can't find D functions that will work everywhere, right? So any D functions that you choose will always fail to span at some point on the manifold. So darn, right? We can't get a basis. Shucks. But we don't go home, we don't give up, right? Because we have another tool, right? Which is a frame. So that's my my FFT part coming in, right? If there wasn't a frame, it wouldn't be a good FFT talk. All right, so so we can't find a basis for all the tangent space, but I really want to do global analysis on manifolds because all this stuff working in local coordinates is annoying, right? And I really want to do it in the eigenbasis. So Whitney says that we can always find 2D functions that are an embedding. And if I've got an embedding, then that means the gradients have to span all the tangent spaces simultaneously. Now they're not a basis anymore because they're overcomplete, right? But we know how to deal with that. Even better is there's this theorem from a 2014 paper, which says that actually if you take enough eigenfunctions, now it's not 2D, and you can come up with examples where it's huge, right? So you can come up, I can write down to you a torus that will need hundreds of eigenfunctions to give you an embedding. But it can always be done if you take, it's always a finite amount. So if you take enough eigenfunctions of the Laplacian, they will give you an embedding into a J-dimensional Euclidean space. And that's sort of the diffusion maps embedding, modulo some scaling. Okay, so I can get, and these are the things that I know how to compute their dot product, right? I have an explicit formula using only structure constants and eigenvalues of the Laplacian for dot products of gradient fields that look like this, and gradient fields that look like this span all possible vector fields in a sense. So we're going to need a frame to do this, and so this is how we do it. So we take a smooth vector field now. Okay, so at each x we get an element of the tangent space at the point x. Okay, but we assume that these vary smoothly. And so now, okay, at each x I can take this guy and I can write it as a linear combination of the gradient fields, gradients of the eigenfunctions, right? So I fix an x and you can write this as some coefficients, but these coefficients are now going to vary over the manifold, right? But I can do it in such a way that they're smooth functions. That's kind of the key fact. So you can choose. So this is non-unique, of course, right? So you have a choice of what these CJs are, but it's possible to choose them to be smooth functions. And since these are smooth functions, that means I can write them in the basis, right? So I take each of those J coefficient functions and I write it as an infinite series. So I've got finitely many gradient fields, but I've got infinitely many eigenfunctions here that decompose the coefficient functions. And so ultimately we see that every smooth vector field can be written not uniquely, but as a linear combination of phi I grad phi j's, where those are eigenfunctions of the Laplacian. So now we can get all the vector fields, right? Not uniquely, although it's a frame. so you can get the frame coefficients, and that would at least give you a unique choice. So this was the theorem that we proved. It's quite a simple theorem. I think you basically need Cauchy-Schwarz and some facts about inverses of matrices, linear algebra. It's quite a trivial theorem, but I think the issue was just that, you know, sort of the people who do frame theory and the people who do differential geometry hadn't talked to each other yet. And so, but that was the cool theorem, right? Is that the collection of all these phi I grad phi j's is a frame. And so we can now start to think about representing operators in this frame. All right, so this is where the spectral exterior calculus takes off, right? We say we're going to try to write everything using eigenfunctions, and in fact, pretty quickly we can dismiss the eigenfunctions and just replace them with structure constants and eigenvalues of the Laplacian. And from this, our first accomplishment was basically to get the matrix representation of the Hodge Laplacian on one forms. So there's a Laplacian on functions, right? This is what we call the zero Laplacian. There's also higher order Laplacians that operate on higher order differential forms. And the first one to go after is the Hodge Laplacian on one forms. And that would give you a basis, essentially a basis of eigenvector fields of the Hodge Laplacian. And that would essentially give you a Fourier analysis on vector fields, because there's an L2 space of vector fields. All right, but we wanted to build this beautiful calculus, right? So we went to town creating formulas, right? So this was the one that we just made. So here's the Riemannian metric, right? And its formula in the spectral exterior calculus is this formula that we just derived. And you can go on and you can start to encode all the other what if you take a gradient of a vector field? What if you take the exterior derivative of some form, the divergence operator, right? So you want to encode all these sort of classical elements in this spectral interpretation. And so this was our big accomplishment, our first big test of the theory, is can we encode the Hodge Laplacian on one forms? And so this is sort of the energy of that Laplacian. And so all we need to do is take that Laplacian, act on one of these phi k grad phi l's, and then take its inner product with a phi I grad phi j, right? And we get some crazy formula that just involves eigenvalues and eigenvalues of the zero Laplacian that we already have, and then these sort of fancier structure constants, but they just involve structure constants and eigenvalues underneath of it all. All right, so we wanted to, so we have this frame, right, for vector fields or differential one forms, but we wanted to get back to a basis, and so that's where the idea was like, okay, you have to sort of use this frame phi I d phi j to get to do anything, because that's where you can write down formulas, right? But then once you can write down the formula for the one Laplacian, now you can take its eigenvector fields, and that gives you back to a basis, right? Now you're back to a basis for L2. And so that was why that was our first priority. And so, yeah, so we went out and did that. And so this is some tests. So this is a flat torus. I'm showing its projections into theta and phi space, which are both just circles. And so this is showing that, when we build our Hodge Laplacian, it's getting the spectrum of the Hodge Laplacian compared to so this is a simple example where you can actually compute the real spectrum of the Hodge Laplacian. Otherwise, if you write down any sort of non-trivial manifold, it's almost impossible to find the spectrum of the Hodge Laplacian. But on a flat torus, you can find analytically the right answer. And so we could check to make sure that the formulas are really working. And yeah, so then you get these eigenvector fields. So, and there's this correspondence theorem that says that the kernel of the Hodge Laplacian corresponds to the homology. And so each harmonic form should correspond to a unique homology class. And so these are the d theta and d phi vector fields that correspond to those homology classes. But then you can just start throwing graphs into this thing and see what you get, and you get cool pictures. So you throw in a Mobius band, and you get so these are the first two eigenvector fields of the one Laplacian on the Mobius. So these should be the smoothest vector fields that you could draw on this Mobius. Now, of course, this is all based on just taking these points on a manifold, discretizing it, turning it into a graph, building a harmonic analysis, and then writing down the formulas from the exterior calculus, and then finding these vector fields. You can also do it for spheres, and we wanted to make sure that our spheres satisfy our vector fields, our smooth vector fields, so they should satisfy the hairy ball theorem and vanish somewhere, and they do. So that looks good. And then you can do it on fractal. So of course we come from the dynamical systems world, so we wanted to try to do this on fractal attractors. These are not manifolds, so none of these formulas make any sense, but you can still use them, and you still get things that sort of correspond to, like, you know, in a sense, this thing has two holes if you were to view it as a sort of rough coarse manifold. And so these are sort of the homology classes of the two holes of the Lorentz attractor, and they are getting sort of pulled out by the eigenvector fields, the harmonic vector fields. Now they don't have eigenvalues of exactly 0, but they have eigenvalues that are close to 0. So, all right, so there's also an argument to be made that maybe this could be useful for, you know, doing things like observability and controllability, solving these higher order PDEs on manifolds. And the argument really goes like this, which is what I sort of said at the beginning, which is that, so there are these two really beautiful, and I don't want to diminish them at all, really beautiful and inspiring competitors to this technique, which are the discrete exterior calculus and the finite element exterior calculus. And there, the advantage that they have is like a lot of the discrete analogs of continuous theorems hold exactly. So things like the divergence theorem hold exactly, right? And the reason that they can make that happen is because they have a simplicial complex. And so they have a notion of boundary, right, that is completely compatible everywhere. We don't have any of that information, right? We just have this graph, right? So we don't have all these higher order simplices to talk about boundaries that are all compatible and things like that. So that's what we give up. We give up a lot of the discrete analogs of continuous theorems, right? But the benefit is all we need is a graph, right? And graphs are really easy to build. Simplicial complexes are really hard to build. There's also another advantage, which is in terms of complexity, which is, this is what I was trying to do, something like the discrete exterior calculus and prove convergence to an analog of the one Laplacian. And what I was finding was that, like, in order to build my one Laplacian, well, I had to like have, you know, vector fields where, you know, at every point you have to have, you know, a vector encoded, right? So now you have like number of points times number of edges, essentially giving you, you know, giving you your encoding of a vector field. And then you want to build an operator from vector fields to vector fields. Well, that's going to be an nk by nk. And if you want to do this on like on S forms, now it's going to be nk to the S by nk to the S, and it just runs out of control. So the really cool thing that the SEC does is you decouple your complexity from the number of data points, because I can decide at the very beginning how many eigenfunctions I want to truncate on. Okay, and you can actually do something really clever where you say, like, I'm going to build, you know, because like I choose phi I and phi j, I and j, you know, j has to run up enough that I get an embedding, right? And I am ultimately going to have to do some kind of truncation because I can't run it to infinity. But yeah, so I think that's all I wanted to say, actually. So I'll stop there. Oh, I should say that these have some really cool topological consistency proofs that goes back to them having a simplicial complex, and we have sort of an asymptotic version of that, but not exact. So thank you.
Thank you. Ladies and gentlemen, a question.